Good morning, everybody. We are going to talk about confidence interval today. We will continue talking about it. And the last couple of topics that we discussed were sampling distribution and central limit theorem. Just to refresh your memory on this thing, sampling distribution is the distribution of the sample means for a specific sample size. So if you have a population, and from the population you pick a random sample of size n, okay, n is some number like 1, 2, 3, 4, 5, 6, right? And typically is bigger than 1, okay, an integer. So if you take a sample of size n, let's say 100, okay, so sampling distribution would be all the possible samples that you can take from the population of size 100. The average of each of these each samples will have a distribution that is called the sampling distribution, and it will look like bell-shaped. So let's say there are many samples of size 100 from the population that you're considering. And from that population, if you take all the possible samples of size 100, and for each of them you find the mean or average, and you graph them, that graph is going to look like this, or that distribution or shape is going to look like this, and this is called the sampling distribution. Now, sampling distribution has a mean, which is denoted by mu sub x bar, okay? This little x bar in the bottom right. So mu sub x bar, that means mean of this sampling distribution with sample size, let's say 100, is the same as the mean of the population. For the population, remember, sample size is 1, okay? This is your population shape. That's one thing. Another thing is the standard deviation of the sampling distribution. That means standard deviation of this shape or this distribution is related to the standard deviation of the population. So sigma sub x bar is equal to sigma divided by square root of n. That means sigma, the population standard deviation, divided by the square root of the sample size. Okay, so that is the sampling relationship between sampling distribution standard deviation and population standard deviation. And that's what it is. So these are the two conclusions of the central limit theorem. And we did it for mean. Similar conclusions could be made for the proportion. Proportion means percentage, right? Proportion. Okay. Now we are going to do the confidence interval for three things: P, M, and S, PMS. We are gonna do confidence interval for proportion, population proportion. We are gonna do confidence interval for population mean, and we are gonna do confidence interval for population standard deviation. So these are the three things that we are gonna do confidence interval for. Now, let me go ahead and continue with this. Before I move on, any question, anybody?
No.
Okay. In that case, let's move on to the confidence interval. So we just started confidence interval last time. So to be comfortable in understanding these concepts, we need to define a few things, or you need to understand some basic definitions that go with confidence interval. One is point estimate. The point estimate is a single value derived from sample to estimate the population parameter. So remember, in statistics, we are collecting data or sampling, right, from the population, and we study or analyze the sample to make reasonable conclusions about the population. To make reasonable conclusions about the population. So basically, you go from sample statistic. Sample characteristic of a sample is called statistic. Statistic, and from there you go to population characteristic, which is called parameter. From statistic, you try to make conclusions about the parameter. That is what it is, okay? From statistic, you go to parameter. Point estimator, that's the formula that is used to find out the statistic, okay? Find the value that you're looking for from the sample. So for average, you find X bar, okay? For sample average. For sample mean, you find the P hat, right? Sample standard deviation, you find S. Sample variance, you find S squared. And the corresponding values for the population parameter. So what is the corresponding symbol for population parameter that goes with X bar? Anyone wants to say that? Araceli? Araceli? Okay. Jonathan Martinez? Okay. So the population parameter, I said it probably at least 5 times, at least 5 throughout the semester. You need to be very clear about these things. So the population parameter is mu. For P hat, sample proportion corresponding to that population parameter is P. For standard deviation, sample standard deviation is denoted by S, and the population standard deviation is denoted by sigma, the Greek letter. Sample variance is denoted by S square, and the population variance is denoted by sigma square. These letters are Greek. This P is probably Greek too, I don't know. Greek typically. These are lowercase English. So please do make sure that you understand these things. So find the point estimator for population mean, okay? So we find the corresponding sample statistic, right, mu. So for mu is estimated by the X bar. X bar is the sample mean, so X bar. This is just lowercase. And for population proportion, this is nothing but the formula for finding average. You add the numbers and divide it by the total number of data points. And for proportion, X is the desired outcome divided by the total trials or total number of times that has been tried. So that's the proportion. For example, you surveyed 100 people and 30 of them said they support abortion. So your proportion is going to be 30 over 100 or 0.3. Now remember, this number has to be between 0% and what? 100%. or equivalently, this is between 0 and 1. This is between 0 and 1. Now for sample variance, S squared, this is what the formula that we use for sample variance. And of course, the corresponding population parameter is sigma squared. That's what it is, okay? So again, the parameter space, these things, by the way, I did talk about it last time, so I'm just going to continue with it just to make sure that you guys see it once more. All right, these are basic definitions, and I will be using these things as I solve the problem, as I create the confidence intervals. So unless you are familiar with these definitions, you might find it challenging what I'm talking about. So I'm trying to make sure that you understand all these things, all right? Parameter space is the set of all the values that the population parameter omega can take. This is the general term that we use, omega, okay? The Greek letter omega is used for parameter space. That means all the values that it can take. So if you're talking about proportion, this would be a parameter space, meaning it would be a number between 0 and 1, including the boundary points 0 and 1. And then if you're talking about GPA, the parameter space for the GPA would be between 0 and 4, including the boundaries. So depending on the context that you're dealing with, parameter space will change. It is not a fixed number. It is context dependent. All right. And unbiased estimator. So if you have an estimator, okay, point estimator, expected value of the point estimators, if that is equal to theta, okay, so then we say it's an unbiased estimator. For example, expected value of the X bar is equal to mu, okay? Expected value of the X bar is equal to mu. Expected value of the P hat is equal to P. So these are unbiased estimators. Or the expected value of S squared is sigma squared. However, expected value of S is not equal to sigma. So this is not an unbiased estimator, not an unbiased estimator. Not an unbiased estimator. Whereas this one are unbiased estimator. All right, these ones are unbiased estimator. Okay, good. Any question, anybody that you may have? Anything? All right. Next, confidence interval. We talked about confidence interval is an open interval of the form A comma B, okay? To this confidence interval, we assign something called confidence level. Okay, there's the percentage that you associate with this confidence interval, that this interval will contain the population parameter that you're dealing with, okay? In this case, population proportion. So there's the confidence level. And there is something called confidence coefficient. coefficient. The confidence coefficient is the probability that this confidence interval will actually contain the population proportion or population parameter. Now you can see how I am using the parameter, population parameter, okay? These are the terms that you'd have to be pretty familiar with in order to make sure that you understand what I'm talking about. Okay, confidence coefficient is the probability that the confidence interval that you created will contain that true population parameter. Now, when you express it in terms of percentage, it's called the confidence level. Confidence level is when you express confidence coefficient in terms of percentage. And we use central limit theorem, sampling distribution, and central limit theorem here as well. Now we have made conclusions about the central limit theorem, 2 conclusions, okay? We have made 2 conclusions about the central limit theorem. One was that mu sub x bar is equal to mu. Similarly, mu sub p hat is equal to p, okay? So that's the corresponding conclusion for proportion. And when does this condition hold true? When this is true. And p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. And I have made this correction last time. So please make sure that you have this fixed. So the product of n times p has to be greater than or equal to 10, and product of n times 1 minus p has to be greater than or equal to 10. All right, so that's what it is. Now let's go ahead and continue. For standard deviation, for mean, we had sigma sub x bar is equal to sigma divided by the square root of n. For corresponding relation for proportion is sigma sub p hat is equal to square root of 1 times 1 minus p, all of it divided by n. Sigma sub p hat is equal to 1, p, not 1 times, sorry, p times 1 minus p. P times 1 minus p divided by n, all of it taken under a square root. So these are the 2 corresponding relation or conclusions of central limit theorem, but for population proportion, and these 2 are for population mean. Okay, so these 2 are for population mean, and these 2 are for population proportion. Now, this is kind of like the theory behind creating confidence interval. Now, if we do this, I'm not going to go deep into it. It has normal distribution z is equal to p hat minus p, all of it divided by square root of p times 1 minus p divided by n. That has approximately normal distribution with a mean of 0 and standard deviation of 1. Once again, this is another thing you may want to make sure that you are clear on. A normal distribution with a mean of 0, mu is equal to 0 and sigma is equal to 1 is a special type of normal distribution. It is called standard normal distribution. Standard normal distribution. And your standard normal distribution table that you look at, that we are making the assumption that mean is 0 and standard deviation is 1, or it is standardized version of the normal distribution. Hence, we call it standard normal distribution. Okay. All right. There's a little bit of explanation here. You may want to read it if you'd like. Okay. You can see this is just a qualitative analysis. This z is equal to p hat minus p. Okay. P hat minus p, that value actually approaches 0. Okay. Because p hat, it gets closer and closer to p if your sample size increases, right? So this value approaches 0. So that's kind of like giving you a sense that the mean is going to be 0. So you have normal distribution with a mean of 0 and standard deviation of 1. All right. Let's move on here. And the formula. So this is what the derivation of the formula. I'm not going to go too much deep into it, except for that confidence interval is found by p hat plus or minus e, which is the same as p hat minus e, comma, p hat plus e. All right. P hat minus e, comma, p hat plus e. What is e? Is called the margin of error, and e is z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by the sample size. So there's gonna be your confidence interval. This has the form a comma b. It has the form a comma b. Now, how do you find z sub alpha over 2 and p hat and n and all these things? You're going to learn it right now. So we kind of got you prepared up to this point to do the actual confidence interval. Once you do a couple of problems, you'll find it rather quite easy. Trust me, it's going to be very easy. And this is one of the things that I'm going to be asking you in the next midterm as well as on the final. So you will have questions from confidence interval as well in the second midterm as well as in the final. And second midterm 2, by the way, just to let you know, I think I already sent an email. Midterm 2 is going to be April 14th. April 14th, which is a Wednesday, like the standard stuff that we did last time. I'll open it up at 6 o'clock in the morning, and you will have until 11:59 or midnight that day to work on the midterm. And the problem structure and everything will be exactly the same. Problem structure and everything else would be exactly the same as the first midterm. Okay. So let's do an actual problem. In order to get an idea about the true population proportion, so see, I'm using these terms already. Proportion, true population proportion, okay, of iPhone users in the US. Apple surveyed how many people? 200 people. So that should be your sample size N. So Apple surveyed 200 randomly selected people who use smartphone phone users and found that there are 120 that used some version of iPhone. So they surveyed 200 people and found that 120 actually use some version of iPhone. So this is going to be your X. You surveyed 100 people, and out of that, X of them or 120 of them responded in a certain way that you are looking for. In this case, you are looking for people that are users of iPhone. So create a 95% confidence interval for the true population proportion of iPhone users among the smartphone users. True population proportion of iPhone users among the smartphone users. Once again, here what we are doing, oh sorry, not X. We are finding the sample proportion. So this is your sample proportion. And from that, you're trying to estimate, okay, estimate P, which is the population proportion. Okay, your P hat is something you're going to get from the sample. And from that, you are estimating or creating, in this case, an interval, an open interval of the form A comma B, right? An open interval of the form A comma B that's going to contain the population proportion. You don't get exact value. You cannot say that, oh, I'm going to find P hat that's going to be equal to P. And that's in general not true. Always, pretty much always is probably going to be different. So P hat is not going to be equal to P, but our objective is to get P hat as close to P as possible. And now the population parameter here we are talking about is the population proportion, and P hat is the sample proportion. So from sample proportion, we make conclusions or predictions about population proportion. Now, our confidence interval is going to be P hat plus or minus E. Okay. Now, I told you E is Z sub alpha over 2 times square root of P hat times 1 minus P hat, all of it divided by the sample size. Now, what is P hat? So we have to find this E, and then once we find the E, we have everything that we need in order to find the confidence interval. So now remember, P hat is defined as X over N. If you recall, I have done it here somewhere. See, there you go. So these things build on top of each other. So it is important that you be familiar with the basic stuff and then go on progressively into more difficult stuff. So these definitions are crucial for you to understand. So let's go back to the problem. Okay. So P hat is X over N. As you read the problem, you saw your X is 120, your N is 200. So there's gonna be 3 over 5, okay? 3 over 5, which is 0.6. So your P hat is 0.6. Now, what is the confidence level? The confidence level, okay, is 95%, okay? So what is alpha? Alpha is 1 minus the confidence level, which is, by the way, is called significance level. Significance level. Alpha is 1 minus the confidence level, which is called the significance level. All right. Okay. All right. So I just introduced another term, significance level, which is 1 minus the confidence level, all right? 1 minus the confidence level. Now, this is another term you guys have to remember, significance level I will be using. I know I do apologize, guys, but it is the nature of the beast that you're trying to tackle here. Is that, excuse me, it has a lot of definitions, statistics. You know, when I took statistics for the first time, I did not like it, learning all these definitions and this and that. Just be patient and it'll all come together like life. With all the ups and downs, at the end it comes together. Okay, I'll share with you a story once I finish the problem. So just to make you feel comfortable. So significance level is 1 minus the confidence level. 1 minus significant level is denoted by alpha. So let me take the background off. So alpha is going to be 1 minus 95%. Okay, alpha is equal to 1 minus 0.95, which is alpha is equal to 0.05. Okay, significance level. So the way you should be thinking is this kind of broadly speaking, significance level is kind of your chances of going wrong. You can think of it that way. There is a 5% chance that you might be wrong and 95% chance that you might be creating an interval that is what? Within the, that is going to contain the population parameter, in this case, population proportion. So you can think of it as your chances of, excuse me, being wrong. So now what does all this mean? So you're 95% confident that you're going to be creating an interval. You're going to be creating an interval that is going to contain the population parameter, and 5% chance that the interval that you're going to be creating is not going to contain the population parameter. So that 5% falls outside. So this region and this region is going to be 5%. So that's what the significance level is. So this significance level we are talking about, that's what the significance level. All right. So now let me speak a volunteer. Where is Jerry? I haven't heard from you in a while. Jerry, are you there, Jerry? I can hear you.
I'm here.
You're here? Okay. All right, Jerry, what is this area?
That's everything outside of the 95% confidence.
Give me a number.
That's the 5.
Give me a number, please. Exactly. That's what I was looking for. Thank you. That's 2.5%, right? 2.5%, which is equal to what? 0.025. And what about this guy? That's also 2.5% or 2.5%. That's equal to 0.025. Now I'm going to pick another volunteer. Let's see. Araceli, are you there?
Yes.
Okay. Can you explain to me, please, why the right side is 2.5% and the left side is 2.5%?
Because if the middle is 95, we need to make it 100%, so 2.5 on each side.
But are you sure that half of it is going to be on the right and half of it is going to be on the left?
No, sometimes it changes.
Sometimes it changes. Okay, good. When does it change?
I forgot.
Okay, good. It happens. I forget to. Let's see, another volunteer. AJ, what do you think?
I have no clue. I'm actually kind of lost.
Oh, you're kind of lost. Okay, actually, Mijan, thank you for responding. I was asking AJ. All right. Anybody else wants to try it? Mercedes, are you there? Okay. Jonathan, what do you think?
I also have no clue on it.
Oh, really? Jerry, what do you think?
Could you repeat the question?
Okay. So question is half of 5%, which you just answered, right?
Yeah.
Is on the right, and half of other half is on the left. Is it always going to be the case or no? If so, when and why?
It's assumed so during the standard bell-shaped curve. But if
You mean bell-shaped or L-shaped?
the bell-shaped curve, like it's assumed that you're gonna have an equal amount on each side because it's evenly distributed. But if you don't get that from the problem, like that, it doesn't tell you that it's bell-shaped curve, you can't make an assumption on the how much is gonna be on each side.
Perfect. Thank you so very much, Jerry. That's exactly the reason. If it is bell-shaped or normal distribution or Gaussian distribution, that's when you're going to have half of it to the right and half of it to the left. Why? Because if your mean mu is here, right? Or in this case, proportion P, right? And it is bell-shaped, it's symmetric, right? It is symmetric. Left is a mirror image of the right, or right is a mirror image of the left. It is symmetric. That's why half of 5% goes to the right and half of 5% goes to the left. Had it not been bell-shaped, you couldn't say that. And why is it bell-shaped? Remember, your sample size, your NP is greater than equal to 10, and your N times 1 minus P is also greater than equal to 10. Even though explicitly I did not show it, but this assumption is there. Okay. We really technically don't know what is P, right? So if we don't know, we kind of assume the middle point, which is 50% or 0.5. So 0.5 times 100, which is going to be 50, that is greater than or equal to 10. And similarly, 1 minus 0.5 times 100, that is also 50, that is greater than equal to 10. So that's what it is.
I have a question.
Yes.
In order for you to figure out if it's normal distribution, the formula, the N times P greater than equal to 10, and then the N with the parentheses 1 minus P greater than 10, does it have to be both or one or the other?
Both. Good question. Okay. Thank you, Mijin. That's a good question. It has to be both at the same time. If one happens but the other doesn't, then it doesn't work. Okay, we cannot make that conclusion. Okay, so now let's go ahead and find this. So now bear with me. It may sound confusing, and it probably does for many of you, but trust me, by the end of the class today, you'll be all good with it, and you'll be like, oh, it's not so bad. So associated with 0.025 area on the left and 0.025 area on the right, there is going to be some z value, okay? And that z value is your z sub alpha over 2. You see, alpha is this. Why do we put alpha over 2 as a subscript to z? Because we are taking half of it, that's why. In our case, z sub alpha over 2 is going to be z sub 0.025. Why 0.025? Because alpha is 0.05. Half of it is going to be, so 0.05 divided by 2, which is 0.025, right? alpha over 2 is going to be 0.025. That means this area to the left and this area to the right. So z sub alpha over 2 is actually z sub 0.025. Okay, z sub alpha over 2 is z sub 0.025. All right, now you have to find that z value. Everybody, please go to the standard normal distribution table and look for an area of 0.025. 0.025, and that's a very common value. You will find it. So everybody look inside the table. Look inside the table, okay, in the value. So there's going to be negative z-score because this is less than 0.5. So it's going to be in the first page. You look for 0.025, the area, that means the probability, and find the corresponding z-score. Everybody, go for it, please. I'll give you like 30 seconds to do that. Everybody, please. I'm gonna go ahead and individually ask you. Okay, what did you get? Anybody can give me the number? I'm gonna find it for you too, but I want you guys to give me the number first. Erica Robles, what do you got? Erica?
I'm not too sure.
Jonathan Martinez, what do you got?
I think I got 0.4920.
You looked at the wrong number, I think. Juan Perez. Juan Perez. Leonardo Lomeli. Anybody else got the value?
I got 0.4920 as well. I don't know how to account for the 5. I can get to 0.02, but how do we account for the 5? Because it doesn't go any further.
You're looking at the wrong value. This is not what I asked you to look at. You are giving.
To look for 0.025.
Yes, that's the exact value I want you to look for. But where do you look for it? Do you look in the first column and the top row, or you look inside the table? I wanted you to look inside the table.
Oh, got it.
Okay, so go back and look at it, everybody. Inside the table, what you're giving me, but just by looking at the column, first column. Everybody, take a moment and do it, because you need to be able to find it. Otherwise, you will get the problem wrong. Another few seconds for everybody.
Is it negative 1.96?
Who is talking?
Megan.
I love that answer, Mijin. Anybody has another lovely answer like Mijin does?
I got the same thing.
Me too.
Okay, me too. All right. That is the answer. Correct. Thank you. So let's go back. I'm going to erase everything from here for the second, and I'll bring it back. I'll have to go back all the way to the top. By the way, for the midterm, you guys should keep this table in front of you. Okay, it has all the formulas. So keep it open in a window, or if you want to, you can print it. Okay, so now let me go ahead and do this. You look inside the table. Oops, what happened? You look inside the table and you look for a value that is closest to 0.025. So this is a special value. It's not too far off 0.025. You will get the exact value. Okay. And where is it? 0.025 right here. And it goes with negative 1.9 and goes to the top 0.06. So it should be negative 1.96. It should be negative 1.96. And that's how you find the value. On the other hand, you guys, I think you are looking at 0.025 on the first column, which is incorrect. Okay. So make sure that you understand what you are looking for. In this case, you are given the probability. You are looking for the z-score, as opposed to many times you are given z-score, you are finding the probabilities. And I told you, this is an important distinction. You need to be able to find out which one is what is given and what is it you're looking for. So let's go back to where we were. Okay, here is my, almost, here is my problem, okay? Oh, no, I went too far, sorry, did I? No, confidence interval. Okay, there it is, sorry. All right, so let's go back to the problem. So this is, so I'm gonna write it in green so that you can see it. This is gonna be your negative 1.96, and by symmetry, this is gonna be positive 1.96. So this is technically negative z sub alpha over 2, okay? This is negative, what happened? No, go away, okay. So this is negative z sub alpha. Hold on, guys, 1 second, something is funny happening. Oh, no wonder why. Okay, this is negative z sub alpha over 2, and this is going to be positive z sub alpha over 2, or z sub 0.025 in this case, 1.96. So you found the z sub alpha over 2, all right, okay, and you found the p hat, you have the n, you have everything. So you just calculate the margin of error. E is equal to z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by the sample size, or E is going to be z sub alpha over 2, which I found 1.96 times square root of p hat, which is 0.6. Remember, our p hat is 0.6. So 0.6 times 1 minus 0.6. All of it divided by the sample size, I think, which was 200. So it's going to be E is equal to 1.96 times square root of 0.6 times 0.4 is 0.24, by the way. Okay, because 1 minus 0.6 is 0.4, 0.4 times 0.6 is 0.24, all of it divided by 200. Now, if you do the math, by the way, I'm going to bring back the screen. If you do the math, your margin of error is going to be 0.0667. So your E is going to be 0.0667. Oh, sorry, 0.0677, sorry, 0.0677. So that's your margin of error. So remember this value. So your confidence interval is going to be P hat plus or minus E, which is the same as P hat minus E, comma, P hat plus E. My P hat was 0.6 minus E, margin of error, 0.0677, comma, 0.6 plus 0.0677. If you do the math, so you will get 0.6 minus 0.0677, which is 0.5323, 0.5323, comma, 0.6677. And that, by the way, guys, is your confidence interval for the population proportion. And how confident you are in this confidence interval? 95% confident that the interval that you created will contain the actual population parameter, which is actual population proportion. What it means is that as an Apple executive, you're thinking, okay, I'm 95% confident that the percentage of people that use iPhone is going to fall between 53 and 66%. Okay, I am 95% confident that the actual percentage of people that use iPhone fall between 53 and 66. Now, excuse me, here is an example where you are using statistics or the knowledge of statistics to make business decisions. Okay, as an executive, you want to know what is your market share like, how you are doing in the market. Of course, they don't do just this simple calculations. They do a lot more sophisticated statistical modeling and calculations. Okay, so this is just a sort of like a very simple example that I gave you to get the concept across. That's what it is. So please make sure that you follow along this thing. Now, this may sound a little bit overwhelming, a lot of information, and you might be thinking, how am I gonna figure it all out? No worries. I'll be doing 4 or 5 different problems of exactly the same type. Then you'll be like, oh, it's not too bad. All right. Before I move on to the next problem and repeat the exact same process, any question, anything in this problem that you would like to ask me?
Could you, this is Mijin, could you repeat what you said at the end after we got the answer?
Okay.
0.4325 and 0.6677. Could you repeat what that meant? You had said something and I missed writing it down.
Okay, that is actually, thank you, Mijin. That is actually an important point. That's kind of the explanation of this confidence interval. What I just said is that this confidence interval that I created, I have 95% confidence that this interval will include the true population proportion, but there is 5% chance that it may not. Now, sometimes people get statistics folks, they get a bit more sensitive about it, but apparently the proper way of saying this thing is this. If you created many examples or many samples of size 200, because our n was 200, right? Okay, size 200, and you created the corresponding confidence intervals. About 95% of those intervals are going to include the population proportion and 5% will not. Okay. However, this is something you need to know, that they really don't like it when you say, if you say, oh, there's a 95% chance that this interval include the population proportion, or the percentage of people that use the iPhone will fall in this interval, and I'm 95, there is a 95% probability. That's not how you say it. You are 95% confident that an interval of this sort, of the same sample size, n is equal to 200, okay, will include the true population parameter, in this case, the proportion. Is this okay, Mijin? Does it make sense?
Yes, thank you.
And remember, along the same note, that 95% confident means what? 5%, 100 minus 95, 5% chance, or 5% of the times you will be not correct, meaning that the confidence interval that you created will not include the actual percentage of iPhone users in the population. Anything else that I could answer for anybody? All right. Let's move on to the next problem. And again, we are going to do the exact same problem, just the numbers changed. Okay, so that you get a feel for it. Exact same problem. In order to get an idea about the true population proportion of iPhone users in the US, Apple surveyed 100 randomly selected people. So that should be your N as you read the problem. So N is 100. Okay, found that 65 of them use iPhone or some version of it. So that should be your X. Create a 95% confidence interval. What that means, your confidence level is 95%. Right away, you should be thinking your significance level is 1 minus 95% or 0.95, which is 0.05. That's your significance level, alpha. Okay, so you need to create the confidence interval. The best way to do it is just by creating the bell-shaped curve first. And here you have to make sure that NP is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. And our N is 100 and we don't know P, right? So we kind of take the mid ground, which is 50, that is greater than or equal to 10. And 100 times 1 minus 0.5 is also 50. That is also greater than or equal to 10. So we kind of approximately assume that. So now what it is we are gonna do, we are gonna create the diagram. The middle portion should be 95% or 0.95. Middle portion is 95% or 0.95. Now, what do you want to do? Find the right side and the left side, which is alpha. So alpha over 2 is going to be 0.05 divided by 2, which is 0.025. It's exactly what we had last time, 0.025. Similarly, this is 0.025. And we don't need to do the calculation too much. It's going to be z sub alpha over 2 negative is equal to negative 1.96, which you just found, and z sub alpha over 2, which is z sub 0.025, is going to be 1.96. Now you can already probably get a feel for the problem that, oh, yeah, it's not too bad. So you found the z sub alpha over 2. Now your confidence interval, I'm going to write it down here, p hat plus or minus e, that is going to be p hat minus e, comma, p hat plus e. Okay, now what is my e? Remember, the formula for e is z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by the sample size n. Okay, p hat, z sub alpha over 2, we found it, right? 1.96. P hat is equal to x over n, which you already have. X is 65, n is 100, which is just 0.65. So you kind of have everything that you need in order to calculate the margin of error E. Oh, it's actually E hat. Okay, I just write E. Basically, hat, whenever you see hat, that means it's coming from the sample. So I will just write E, okay? So it's going to be 1.96, maybe to be precise, E hat times square root of P hat is 0.65. 0.65 times 1 minus p hat is 1 minus 0.65, which is 0.35. So 0.35. All of it divided by the sample size 100, right? Now, if you do this calculation, your margin of error is going to be, so let's do the calculation. 0.65 times 0.35 divided by 100 is equal to this to the power 0.5, which is 0.0476. 0.0476. Okay, if you round it to this digit, it's going to be 0.0477. Just leave it as it is. So 0.0476. Okay, now actually let me just round it. Sorry, 0.0477. So your margin of error, confidence interval is going to be p hat is 0.65, right? 0.65 minus the margin of error 0.0477, comma 0.65 plus 0.0477. So let's see, 0.65 minus 0.0477 is 0.60, 0.6023, comma 0.0477 plus 0.65 is 0.6977, 0.6977, which, by the way, equivalently could be written as 60.23%, comma 69.77%. Now you can see that it's so easy to find the confidence interval. Now this confidence interval that you have created, how confident are you in it? You are 95% confident that this interval is going to include the true population parameter or population percentage in this case. So the percentage of people that use iPhones in the US would fall between 60.23% and 69.77%. How confident are you in your calculation? You are 95% confident. How confident are you that this interval, the actual percentage of people that use the iPhone would fall between 60.23 and 69.77%? You are 95% confident. What does this mean? If you were to take many samples of 100, size 100, and for each of these samples, you created an interval like this, let's say you created 1 million of them, let's say 10 to the power 6 of them, right? Out of that, 95% of the intervals, okay, which is 950K, okay, will include the actual percentage for the population, whereas 50K will not include. That is what it means, this confidence level, okay? So I have done exact same problem with the numbers changed. Now, how many people feel that you really followed this one slightly better? You feel slightly more confident? Do you feel a little bit more confident in solving, finding the confidence interval?
I feel a little more comfortable with it, but I haven't really quite memorized the different formulas to solve for different things like p-head and stuff. So when I'm trying to follow, it's a little fast for me. So I guess I just need to memorize those separate little formulas and understand what I need to solve for in what order.
Yeah, as you do more problems, these formulas are gonna come into your working memory, what we call working memory. Okay, memory that you locally use. It's kind of I just wanted to share a story with you, and I will now. I think this is a good time to share that story. I'm an engineer, actually. Many years ago, I used to work as an engineer. And I used to work on designing the CPU, so Central Processing Unit. That is the brain of the computer, okay? Every computer has a CPU. Now, it may be a simple one or a complex one. Even your iPhone has a CPU, okay? Your laptop, desktop, and your TV technically has some sort, we don't call it CPU, but it has some sort of CPU type thing that creates the what? That makes you do a lot of calculations, okay? Those are called edge devices. Edge devices, okay? Now, anyway, CPU for the computers, okay? I used to, back in those days, in early 2000, I was fresh out of college around that time, actually, right before 2000. I started working as an engineer. So my office was next to the guy who was the chief architect for the CPU. He's like the main boss for designing the CPU, okay? He gives the architectural structure that makes the CPU go faster, do better things. And so there are like a couple of hundred engineers who are working with him in some capacity. So we one time he said this thing after we finished working on a CPU. He said in a meeting, you know, when you start working with the CPU, there are so many ways things could go wrong, okay? When you actually design a CPU, there are so many things that could go wrong. If you think of in terms of common sense, let's say you're given this project and there are so many things that could go wrong, initially you'd be thinking that, my goodness, there is no way we can get it right. But somehow, at the end, it all comes together and it actually works. So why am I telling you this story? Because your course, statistics, it may sound overwhelming and lots of information, things don't stick and this and that, but keep hanging in there and it will come together at the end, okay? It's just when you're in the middle of the tunnel, you don't see the light. It feels all dark and you're losing hope. But at the end, there is light. Speaking of that, I have to share a joke. Another This is kind of funny. This was told by a student of mine, and she was so funny. One time, again, I was saying the same thing. And I told her that, don't worry, there will always be light at the end of the tunnel. Okay, so keep going. Then she said, I hope it's not the headlight of a train. So I thought that was pretty hilarious. So anyway, there is hope at the end of the tunnel. There is light. So don't give up. And you guys, you may or may not know, when we design CPU that goes into the computer, which does all the calculations, there are many ways things could go wrong. You just don't know about it. As an end user, you don't know. But if you're a sophisticated engineer and you really know how CPU and operating system work together, you can go ahead and target those vulnerable points. And that's exactly what bugs are. So mostly software related, how things don't work out. It's most of the times it's OS related, but there are ways you can manipulate things, and it's not very easy to do so. Okay, and normally it is done through the software, because on the CPU runs the OS or the operating system. Okay, if you don't directly access CPU, but you through OS when you're using Microsoft Word or when you're using Zoom right now, right? It's an application that's run on OS, right? It's an app. And then that application goes to the OS and CPU does the calculation for processing the actions. So through this app, through the OS, you can get access to the CPU. So anyway, I still remember in my early days, younger days, that architect's story. He said, look at the beginning, it looks like we will never make it, but somehow we do. All right, enough. Let's go back to our problems. Next, let's do this. And there are probably 3, 4, 5 problems, maybe 6 problems, and I'm going to do all of them. Okay, and I'm going to do them slowly, take my time, so that you guys can feel confident. Once you get the hang of it, you will find rest of the semester very easy. Okay, because hypothesis testing is going to be very, very similar. Once you understand the confidence interval for this population proportion, you'll understand the confidence interval for population mean, you'll understand the confidence interval for population standard deviation. You just need to understand one, because structurally all of them are the same. Structurally they are the same. So once you get the hang of one of them, the rest will come together. As I read the problem, next one, okay, cyberbullying is a major issue in today's social media networks such as Facebook, Twitter, and Instagram, Snapchat, TikTok. I should add TikTok here. Okay, Pinterest or this and that, many social media networks. You are curious about the true population proportion of social media users that were cyberbullied. As you know, in the social media, people are being bullied, even in the professional level. Like you see nationally news. We don't have to go too far. Our lovely president has done it many times, and that I should say ex-president, right? He lived off of Twitter, and he did bully people. That's a well-known fact around the globe. But anyway, this is a major problem. Okay, I know just the other day I was reading an article. I don't know if she's a model or an actress or something, or a singer. She got off she got off Twitter and or Instagram because of bullying. One individual I particularly remember, Selena. Is her name Selena? Selena Gomez, who was what's his name? From the Canadian singer, his ex-girlfriend, I forgot her. Justin Bieber, Bieber's ex-girlfriend. She once mentioned that social media is very distracting, and psychologically it takes a lot of toll on people. And it is true. For them, it's at a bigger scale. For you, among the friends that you are on Instagram, people make comments, people criticize, people do this, that, this or that. You have to be always respectful and digitally correct, okay, in social media. Make sure that you're respectful to other people. So cyberbullying is a real issue in our society, okay, that didn't exist like 20 years ago or even 15 years ago as much. Now, to figure out what percentage of the people have experienced some sort of cyberbullying in the past, okay, so what do? You took a survey of 300 people. So right away, you know that your N is 300, okay? You ask them whether they have faced cyberbullying, and 120 of them responded yes, that they have been X. And this time you want to create a 90% confidence interval, not 95%, 95% confidence interval for the actual or true percentage of people in the population who have been cyberbullied. True percentage of people in the population who have been cyberbullied. Now, this cyberbullying confidence interval, again, is pretty straightforward. Let's find the easy stuff first. P hat is X over N. What is it gonna be? Can I have a volunteer for that, please? Some volunteer, please. Mercedes, what is P hat? X is 120, right? N is 300. So you just divide it by 300. So it's 0, 0 cancel out. 6 goes into this twice. 6 goes into this 5 times. So this is 2 over 5 or 0.4. So your P hat is 0.4. Now you have to do the normal distribution curve. Alpha significance level is 1 minus the confidence level, which is 0.9. This time, okay, this time it is gonna be 0.10. So your alpha over 2 is gonna be 0.10 over 2, which is 0.05. So your left tail is gonna be 0.05. And similarly, your right tail is going to be 0.05. All right. And the middle is 90% or 0.9. Now we've got to find this value and this value. You can look it up in the table and you'll see negative z sub alpha over 2 is going to be negative 1.645. This is a special value. You can look it up. And this is going to be z sub alpha over 2 is 1.645. Actually, I'm going to go ahead and take you to that spot. Okay, look right here. Oops. This is a special value right here. The closest value we can get is 2.05 is somewhere between this and this. We average them and that gets you negative 1.645. That's what it is. Okay. Now let me go ahead and go back to the problem. Okay, there it is. So this is your z sub alpha over 2, negative 1.645. So your margin of error, okay, margin of error is going to be z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by the sample size n. So E is going to be 1.96 because this is what we got. Oh, sorry, not 96, 1.645. 1.645. That's your z sub alpha over 2 times square root of p hat, which we found to be 0.4. 1 minus p hat is going to be 0.6. 1 minus 0.4 is 0.6 divided by the sample size, which is 300. Remember, this square root is on the whole thing. Now, if I do this calculation, what do I get? 1 divided by 300, this times 0.4 times 0.6 equals this to the power 0.5 is equals this times 1.645, which is 0.04. That's E is equal to 0.0465. That's what the E value is, or the margin of error. Your margin of error is 0.0465. Now, let me ask you, any questions so far, anybody? Any question about the process? This is more process than knowledge, really. Knowledge part is the theory, which I covered just a little bit, not a whole lot. Is this okay? Everyone following along?
Yes.
Okay. Now, let me continue. So I found my E. So my confidence interval is going to be p hat plus or minus E, which is p hat minus E, comma, p hat plus E, which is p hat is 0.4, right? 0.4 minus 0.0465, comma, 0.4 plus 0.0465. So 0.4 minus 0.0465 is equal to 0.3535, comma, 0.4 plus 0.0465 is 0.4465, which, by the way, is the same as 35.35%, comma, 44.65%. Okay, so that is the confidence interval. You can express it in terms of percentage too. How confident are you that this interval will include the actual percentage of people who get bullied on the social media, or who has been bullied, who has been cyberbullied? So that percentage falls between 35, roughly 35 and 44, or 35.35 and 44.65%. You are 90% confident that this interval contains the actual percentage of people that have been cyberbullied in the social media. And what does that, again, 90% mean? It means that if you were to create many samples of size 300, in our case, n was 300, right? N is 300. If you were to create many samples of size 300 and create confidence interval from them, if you were to take many samples of size 300 and create confidence interval from them, from each of them, about 90% of those confidence intervals will include the actual or true population proportion or true percentage of people that have been cyberbullied in the social media, whereas about 10% will not include. Now, you can increase, who said you have to do 90% confidence level? You could do 95%, you could do 96%, doesn't matter, you pick it, right? You could do 99% confidence interval. What's gonna happen as your confidence level goes up, these intervals are gonna be wider, okay? To get higher confidence, the intervals are going to be wider, but you can make it narrower too by increasing the sample size. If you increase your sample size, then interval is going to become narrower. Your confidence level goes up, okay? That means the interval becomes wider, right? But your sample size goes up, interval becomes narrower. So these are two kind of opposing forces. Well, confidence level, if you want to have higher confidence level, your interval is going to be wider. If you want to have more confidence, of course, makes sense, it's going to be wider, but you can control it by controlling your sample size. And that's exactly what we do, actually. In reality, you increase your sample size to get a better estimation of population parameter that you are looking for. And that's exactly what you do in statistics. As I said, you take a sample, and from the sample characteristic, you try to measure, or rather estimate. Measure is not the right word. Estimate population parameter. That's what it is. Okay, any question? Anybody? Is it okay? Looking all right? No questions? Everybody okay? All right. You know what I will do? I can give you a couple more examples for the day, but I will not, rather. I want you to absorb this information, okay? I want you to absorb this information, and I'd like you to please look at this video and make sure that you do follow along the process and do the examples. There are few examples here, problems that I gave you. There are four or five more left. Try all of them. If you understood somewhat what I have done, you should be able to do all of them. And I would like you to try these problems at home the next couple of days, all right? Then you come back on Wednesday, and I'm going to do all of these problems for you, every single one of them. And if needed, I'm going to go back and do the ones that I already have done. Okay? So I think it's important that you try it on your own. Don't just look at me and, okay, this is how you're supposed to do. Because I have done it 100 times. That's why it comes to me naturally. But you haven't done it before. So you need to practice it on your own. Just follow the example that I gave you and try other problems. All you need to do is this. You need to find n. So let me just give you one particular problem. So look at this problem. Even without reading what the problem is, okay? From this one, you could probably see your n is 50, your x is 20, and your confidence level is 0.80 or 80%, or alpha is equal to 1 minus 0.8, which is 0.2. See how quickly, I haven't even read the problem. Just by looking at the numbers, I can guess these are the numbers. Now, you know that, so your alpha over 2 is going to be 0.1, and you go back and look it up in the table, and they'll give you z sub alpha over 2, or z sub, in this case, z sub 0.10. Okay, this is probably going to be 1.28 if I'm not mistaken. So all these problems are exactly like this. And then you create the bell-shaped curve, and to the left and to the right would be 10% and 10%, right? 0.10 and 0.10, and in the middle is going to be 0.8. So there you go. You got it. All right. So make sure to follow along these examples I gave you. Just find these values, find E, and then your confidence interval is going to be P hat plus or minus E. And that's what it is. And it is pretty straightforward. Okay. In this problem, just something came to my mind. In this problem, when I did the calculation, I hope I multiplied by 1.96. I think I did. That's your Z sub alpha over 2. Okay. In case if I didn't, make sure that you do, because your margin of error is Z sub alpha over 2 times square root of P hat times 1 minus P hat, all of it divided by N. Okay. Just for a second, I'm thinking, when I did the calculation, did I multiply by 1.96? I think I did, but in case if I didn't, make sure to do that. Okay, so any question before I let you go for the day? Anybody? All right, once again, my request is that you look at the remaining problems at least. Okay, please look at the remaining problems, try them on your own, and come back to class on Wednesday. Then we'll go over the problems again. And if you have little time, you can start the next section. In the PMS structure, we did confidence interval for P. We are going to do confidence interval for M, mean, and then we are going to do confidence interval for standard deviation. So on Wednesday's class, I'm going to finish all of the problems, the remaining 5 problems in the confidence interval for proportion. Then I'm going to start confidence interval for population mean. Okay. And if you want to get a head start, you may want to look at it and try 1 or 2 problems, like check it out, you know, it's kind of like the same thing. Here is an example that I did. You could follow along that example. It should be pretty straightforward. All right, that's all for today. Thank you so very much, folks. You have a wonderful day and rest of the week. And we'll talk to you on Wednesday.
Thank you. Bye.
Bye.